Hello everyone, welcome to the video of my final year project on effective gray box fuzzing, instruction level branch condition penetration for beef. I'm Chen Taoyu and my FYP supervisor is Professor Liu Yang. As software has become an indispensable part in our day-to-day life, there is an increasing need of effective techniques to discover software vulnerabilities, and there are many techniques. Fuzzing has remained one of the most widely deployed techniques ever since its introduction in the early 1990s. Fuzzing is conducted by a program called fuzzer. The idea of fuzzing is to send randomized input to the program under test to trigger unexpected behaviors which may reveal new vulnerabilities. The most commonly used fuzzers are coverage-guided fuzzer or coverage-based fuzzer, which focus on finding inputs that cause new code coverage, such as executing a function that wasn't executed before, to explore edge cases that may crash the program. To do this, fuzzers run many different randomized inputs through the target program. Whenever there is a new coverage discovered, the input is used for further mutation. Despite the increasing popularity of fuzzing, there are few issues with existing fuzzers. Firstly, a large number of existing fuzzers require the source code of POT or program under test, which may be hard to get, since the source codes are usually proprietary. Secondly, fuzzers with binary-only support usually rely on heavy instrumentation, which greatly reduce the overall performance. Thirdly, many existing fuzzers are designed to run on a few specific CPU architectures, therefore lack cross-architecture support. Finally, the most importantly, most of the existing fuzzers are coverage-based fuzzers and are less effective for discovering crashes shielded by comparison of magic bytes as shown in the figure. Since coverage-based fuzzer only collect the coverage information, meaning which branch it enters, input being MAZX and XXXX makes no difference to it because both inputs don't enter the if clause. Therefore, the fuzzer can only randomly and blindly mutate the input in this case until input becomes MAZE and the new path is found. Since each character is 8-bit long and there are 4 characters here, it requires 2 to the power of 8 to the power of 4 attempts for input to become MAZE. This is very inefficient. This shows that the coverage-based fuzzers are less effective in discovering this type of common crashes. Stillix is a program state-based fuzzing approach that aims to tackle the issue of comparison of magic bytes. The idea of Stillix is to collect comparison progress information in addition to coverage information. The comparison progress information is used as guidance for further mutation. On the slide is an example of adaptive mutation. For input 1, the comparison progress is 1, meaning that there is 1 byte match for this input. The comparison progress becomes 2, 3, 4 for input 2, input 3, and input 4 correspondingly. Whenever there is a new comparison progress, it will exhaustively try all the possibilities of the 1 or 2 neighboring bytes. In conclusion, the comparison progress information is used to inform fuzzer on how to mutate the input. With this information, it only requires 2 to the power of 8 times 4 attempts for input to become MAZE. This shows that program state-based fuzzing approach are way more effective than coverage-based fuzzing approach in this case. Stillix contains 3 main components: static analysis, binary instrumentation, and the fuzzing loop as shown in the slides. In particular, static analysis aims to find comparison instruction that will be dynamically instrumented and analyzed during fuzzing. In this project, we integrated Stillix into a fuzzer named Beef that supports cross-architecture fuzzing and binary-only fuzzing target. For Stillix integration, we still want to maintain the support for cross-architecture and binary-only fuzzing. Therefore, we utilize Ghidra for static analysis, which is an open-source software reverse engineering tool. And we utilize Scorpio for binary instrumentation, since it is a dynamic binary instrumentation platform utilizing hooking instead of just-in-time translation technique, therefore support cross-architecture and fast execution. We also implement the idea of Stillix fuzzing loop logic and integrate it into Beef. In this project, we mainly focus on dealing with instruction level comparison, as shown in the figure above, rather than function level comparison, as shown in the figure below. The difference between these two types of comparison is that instruction level comparison doesn't use any function for comparison. The reason we choose to focus on instruction level comparison is that the idea of Stillix can be easily applied to function level comparison using hooking, while for instruction level, it requires assembly language level operation, and it is more complex. After we finished the implementation, we evaluated our fuzzer on a sample program which contains a crash shielded by 4 bytes comparison. Fuzzing with instruction level Stillix is able to find the crash within 1 second, as shown in the right side figure. However, fuzzer without Stillix integrated was not able to find the crash even after 1 hour. This shows the effectiveness of our work. In conclusion, in this project, we enhanced the existing fuzzer Beef such that it has high branch penetration power for crashes shielded by magic byte comparison, and it supports fuzzing cross-architecture and with high speed for binary-only target. That's the end of this video. Thank you for watching.